So we know that the Earth is about 4.5 billion years old. And we know that life is a little over 3.5 billion years old. And we know that eukaryotic life is a little over 2 billion years old. But it wasn't until around 530 million years ago that life starts to look a little bit more like it does now. And this is referred to as the Cambrian explosion, because in the fossil record, there was very little large life until this time, and then all of a sudden you see a ton of it. And this was first discovered in a place called the Burgess Shale in Canada, and you see examples of every animal phylum that you see today represented back then. Now, there were lots of organisms that are extinct today, but they represented each of the phyla that we see today. And there were animals before this, but they tended to be soft-bodied, things like sponges. There were some cnidarians. There were some mollusks. But the volume of animal life and the diversity of animal life wasn't seen until this Cambrian explosion. The Cambrian explosion also shows the first evidence of predator-prey interactions. Oh, what is evidence of predator-prey interactions? Well, you start to see things like teeth and claws and the kind of characteristics that you would expect in a predator. You also start seeing protective traits on prey, right? So predator-prey interactions are present at the Cambrian explosion. So as you can see, sponges and cnidarians like jellyfish had been around, but things like echinoderms and chordates, which include us, right? Brachiopods, annelids, arthropods, these things popped up and diversified right around the Cambrian explosion. Now again, there's some evidence that many of those animal phyla may have diversified shortly before the Cambrian explosion, maybe even as early as 700 million years ago, but fossilized evidence begins being very common around this time. Now, after the Burgess Shale was discovered, there was another big set of fossils discovered in China that was tens of millions of years older than the Burgess Shale, suggesting that while there was what looks like this explosion of life, this explosion may have had a long fuse. It may have been a little while in coming. It was shortly after this, relatively shortly, about 500 million years ago, when multicellular organisms began to colonize the land. Up until this point, they'd only existed in the ocean. So this is fungi, plants, and animals. And in plants, you started to see vascular tissue, so xylem and phloem, which we'll talk about later in the semester. These things are strong and essentially give the plant sort of an inner skeleton and allow them to deal with gravity. When you move to the land, you not only have to figure out how to exchange gases differently, you also have to figure out how to deal with gravity because you're not in this buoyant environment like the ocean. So animals also had to figure this out. And the first animals to colonize the land were arthropods. So they have this exoskeleton. So insects, in other words, and spiders, arachnids, were the first to get up in the land. And then tetrapods like us got there about 365 million years ago in the form of lobe-finned fishes. So fish whose pectoral fins had changed their skeletal makeup and become muscular so they could kind of crawl on the land a bit. Now, over the last 3.5 billion years, a lot of forms of life have evolved and appeared, and a lot of forms of life have also become extinct. There's sort of a normal speciation rate and extinction rate that kind of occurs in the background, and you tend to have increasing diversity when the speciation rate is higher than the extinction rate, and when the reverse is true, you tend to lose diversity. Extinctions are a regular part of life, and looking at the fossil record shows that the majority of species that have ever existed don't exist anymore. They've become extinct. And a lot of things can cause extinction. Very often it's a change to a species' environment, or it could be another species showing up and outcompeting them. But from time to time, the rate of extinction increases dramatically. We call these mass extinctions. You generally have mass extinctions in response to some sort of disruptive global environmental change. Now, we call it a mass extinction when more than 50% of Earth's species become extinct. And there have been 5 mass extinctions that we know of in the history of life. Right? So one here at the end of the Ordovician, one right here about 365 million years ago. You notice a big spike here about 250 million years ago, one at the end of the Triassic, and then one at the end of the Cretaceous here. Now, this is probably the one that you're most familiar with. And this, at the end of the Cretaceous, is what did in the dinosaurs, right? But this is not the biggest mass extinction we've ever had. That honor, or whatever you'd call it, belongs to the extinction that happened at the end of the Permian, which is sometimes called the KT extinction. Now, that extinction event defines the boundary between the Paleozoic, meaning ancient life, and the Mesozoic eras. The Mesozoic era is the era of the dinosaurs, essentially. That ended with the extinction at the end of the Cretaceous, which began the Cenozoic era. During this Permian extinction, 96% of marine animal species became extinct. 96%. And we don't know exactly what caused it. There are a lot of hypotheses, and there's some evidence for each, and they're not all mutually exclusive, but there looked to have been some intense volcanism in what we now know as Siberia. Again, it looked different back then because the continents have moved. And CO2 becoming emitted from volcanoes caused global warming. There was a reduced temperature gradient from the equator to the poles, and that temperature gradient is one of the things that causes currents, right? Heat causes expansion, cold causes contraction, cold causes sinking of water, heat causes rising of water, and all those things cause ocean mixing. And this lack of a gradient caused anoxia, right? A lack of oxygen in the waters, which could contribute to mass extinction. Now, you're probably more familiar with the Cretaceous mass extinction 65.5 million years ago. That's what separates the Mesozoic from the Cenozoic. Again, Mesozoic being where the dinosaurs existed, Cenozoic being now, right, from 65 million years to now. And a lot of organisms went extinct, about half of all marine species, a lot of terrestrial organisms as well. And it's thought, and there's a lot of evidence to suggest, that this was caused by a meteorite impacting the Earth around that time. And one piece of evidence for that is that there is a layer of iridium in sedimentary rocks all around the Earth from about that time. Now, iridium is not very common on the Earth, but it is more common in meteorites. And this suggests that meteorite hit, and there was an explosion, and then dust was in the air and then settled all around the Earth in this sedimentary rock in very, very high concentration all at once. And so this would obviously cause a concern right where it hit, because you'd have a giant explosion, right? All that energy and heat boom, hitting the Earth would cause a big explosion. But also then dust clouds would have risen and would have blocked sunlight and disturbed global climate. You would have had very quick cooling off of the world and blocking of light, which obviously makes it harder to photosynthesize, and a lot of organisms would have died. And now scientists have found a crater off the coast of Mexico and the Yucatan that seems to be evidence of a meteorite that dates back to around 65.5 million years ago. And here you can see about where this happened, right? Just off the coast of the Yucatan Peninsula in the Gulf of Mexico. And this is our dramatic illustration of what it may have looked like. Now, right now, the extinction rate is somewhere in the order of magnitude of 100 to 1,000 times the typical background rate that we've measured. And extinction rates tend to rise as global temperatures increase, and we are having a lot of organisms that have become extinct in the relatively short amount of time that there have been humans. And all of this comes together to suggest that we may be under undergoing a sixth mass extinction right now. Now, it's difficult to say because while these mass extinctions feel like they happen immediately, they really happen across millions of years, right? It's a very short amount of time geologically, but it's long in terms of human life. But right now, there's evidence that we are kicking off a sixth mass extinction caused by humans. Here you can see a graph of temperature, right, degrees above or below average, and relative extinction rate of marine animal genera. And as you can see, it tends to go up as you go to the right, warmer. And these are our mass extinctions up here. Again, most of them tended to be warmer, this one being an exception. So in a mass extinction, you've probably had some sort of global upheaval in the environment, and you've had a lot of deaths of organisms, extinctions, and so a lot of niches become available. And so it can take 5 to 100 million years after the mass extinction event for diversity to recover back to where it was, but they do make way for adaptive radiations because you've essentially cleared away all these ecological niches, these places where you can make a living. Once the world begins to recover, new organisms can evolve to fill in those vacant niches. And for some reason that's not entirely understood, there seems to maybe be an increase in the percent of genera that are predators that go up after a mass extinction. So your Permian mass extinction, we had a little bump, although that was maybe starting earlier. After a Cretaceous mass extinction, we see another major bump in the percent of genera, which is the plural of genus, of organisms that are predators. So what do I mean by adaptive radiation? Adaptive radiation means you get a huge diversification. So from a common ancestor, you wind up with a bunch of different species. So not just a typical speciation event or a couple of speciation events, but lots and lots of speciation events, all coming in a relatively short amount of time. And again, these tend to come after mass extinctions because lots of ecological niches have opened up, or after the evolution of novel characteristics. So for instance, when the flower evolved, it was very, very beneficial. And so lots and lots of organisms with flowers spread and created new niches essentially because of that new characteristic, and then they diversified because of all these new niches. Same thing can happen when you colonize new regions. So first of all, colonizing a land, right, can lead to an adaptive radiation, or colonizing new land masses like island chains, things like that. All of these can lead to increased speciation events. And worldwide, you saw one of these after that Cretaceous mass extinction. Dinosaurs disappeared with the exception of birds, which are dinosaurs, and mammals, some of which survived, mostly smaller mammals, ground-dwelling mammals that lived underground sometimes, were then able to, over the course of many millions of years, diversify and take some of those niches that had been vacated by dinosaurs. There have been a lot of other radiations in the history of life. So after photosynthesis was evolved by prokaryotes, cyanobacteria, big radiation. Radiation of large predators in the Cambrian. Again, land plants, insects, tetrapods, all of those after the colonizing of land. In addition to global adaptive radiations, you also have regional adaptive radiations that happen again when you will colonize a smaller landmass or a chain of islands. For instance, the Hawaiian Islands are a great example of an adaptive radiation, right? Just like the Galapagos Islands. And this is an example of one plant that colonized the islands and diversified it into lots of different plants, including this guy, which is a silver sword, is the common name. And I spent a semester at Chaminade University on Honolulu when I was in college, and Chaminade is the Silver Swords. They also host the Maui Invitational if you're a college basketball fan. But a place like Hawaii, where you have several different islands all isolated from the mainland, give an opportunity for incredible adaptive radiations like the one you see here.